Hello everyone. In this video we're going to go into a brief history of the atomic theory and what types of experiments have led to our modern knowledge of the atom, which is important for an introductory chemistry class. A couple things to keep in mind. Atomic theory is just that, it's a theory, so there's a lot of different contributions that we're going to discuss today where changes have been made to previous ideas. And I'll be sure to outline those and give you some detail for all of those circumstances. So one thing I hope that you notice from this slide initially is that we have some dates here. Now you're not expected to really memorize dates for atomic theory because, again, these are all relative. These ideas, for example, Lavoisier had been thought of and thought out well before this, but this was the date of the publish of the paper. So keep that in mind. So atomic theory basically kicks back to 400 BC in Greece with a philosopher named Democritus. He was the first person to coin the term, basically the atom, but the Greek term atomos, which, if you were to describe that, means it's either indivisible, which means it can't be separated or can't be further divided, or cannot be cut, which these atomos make up all matter. So his idea was if you take anything that you're familiar with in your day-to-day life, let's say a piece of grass, for example. If you were to take that piece of grass and you were to cut it in half, you would have two half pieces of grass. And then you take each half and you cut those halves in half. And then you cut those quarters in half, and then those eighths in half, and so on and so forth. And you continue on this for as long as you can. Eventually you get to a point where you physically cannot cut things in half anymore. And when you can't cut things in half anymore, you have to have the fundamental building block that makes up that thing. So the idea was, well, grass has grass atomos or grass atoms, and cheese has cheese atoms, and carrots have carrot atoms, and different things like this. So this was a really unique and fundamental idea. Now you have to keep in mind, in ancient Greece in 400 BC, Democritus wasn't the only philosopher. There were many other prevalent philosophers, such as Aristotle, who had a different perspective of how the world was made up. Their ideas was that, well, if we think of the four quote-unquote core, things that make everything up, you have fire, you have earth, you have water, and other things like that, and that makes up everything. And Aristotle was a little bit more popular, and as a result, that just led to Democritus's ideas kind of being forgotten in the wind. So let's fast forward a couple thousand years, and we have a French aristocrat, very wealthy person, Lavoisier. He was a tax collector during the French Revolution, so not the best occupation to have at that time. He loved doing science in his spare time, in his hobbies, and he commissioned a pretty big lab. And what he found was several experiments of gases and fire and things like that, that whenever you do a chemical reaction, whatever you start with, if you're able to trap the gas, you finish with that same amount of stuff as well. Nothing is lost. No mass is created nor destroyed in a chemical reaction. If you start with 10 grams, you're going to finish with 10 grams. And that was his first contribution to atomic theory. Now you're probably wondering, well, this doesn't outwardly have anything really to do with atoms from the term law of conservation of mass, but the idea is prevalent when Dalton really derives his 5 postulates about how things are connected. 20 years later, we have Joseph Proust, who came up with the law of constant composition. And basically what this means, and this is also referred to, you might see it as the law of definite proportions. And what we find is that if you have something that's unique, let's say water, for example, if water is pure, all water is going to be made of the same fundamental ratio of stuff. So basically this was the idea of if you were to do a mass calculation for, how much of the element hydrogen and the element oxygen are in pure water, it would be the same percentages every single time. And the definite proportions piece kind of plays into it. It's got to be a whole number. So these two laws were basically used to support Dalton's modern atomic theory. Now, Dalton is known as the father of the modern atomic theory, because he was the first person that kind of linked all these three ideas up together. He linked up Democritus's ideas, Lavoisier's, and Proust's all together. Now, what do we mean when we say modern atomic theory? It's not having anything necessarily to do with the year, but rather it's the way in which the atomic theory was derived. Notice, Democritus was a philosopher. He did no experiments to support any of his claims. He had no evidence. It was basically his ideas versus everybody else's. And that's basically a popularity contest, and that has no merit in the validity of whatever he's saying. So, with modern atomic theory, basically what this means is that everything that Dalton discusses is testable, which means you can actually do it in experiments. You can do it in a lab. You can repeat things over and over and over again, and you can get conclusive or perhaps non-conclusive results. So let's go into those 5 postulates. These should all look pretty familiar. The first thing we have is that elements are made from tiny indivisible particles called atoms, which cannot be created or destroyed. Again, this kind of goes back to Democritus's claim. All atoms of any given element are identical in mass and size. The atoms of an element are different from atoms of other elements. A chemical reaction results in the rearrangement of atoms in the reactant and product compounds. And lastly, compounds are produced through different whole number combinations of atoms. Now again, what's important about these 5 things? They're all experimentally testable, which is important because that's what makes Dalton's atomic theory a modern atomic theory. And then what's nice about having them being experimentally testable is that you can perform additional experiments to revise some of these things. So as I was reading these 5 postulates, some of these may have seemed kind of fishy to you because we know with our modern knowledge of chemistry that not all of these are entirely true. We know that atoms aren't the smallest thing that makes up elements. We know that within an atom, we have protons, we have neutrons, and we have electrons, right? So these subatomic particles together make up an atom. And then those atoms basically can identify as different elements depending on the number of protons that those atoms have. The next thing that's kind of fishy to us is number 2, because we know that all atoms of any given element are not identical. And how do we know this? We can use isotopes to support that claim. Because isotopes essentially are atoms of the same element, however, they vary in the number of neutrons. So if you think about it, popular isotopes include carbon-12, carbon-13, and carbon-14, right? So these are 3 isotopes of carbon. What's different about all of these 3? It's the mass number, 12 versus 13 versus 14. Now, what's common about all of these is they all have 6 protons, right? In order for carbon to be carbon, it has to have 6 protons. If you look at a periodic table, that little number on top, that's your number of protons. So if all carbons have 6 protons, that means this carbon has to have 6 neutrons, this carbon has to have 7 neutrons, and this carbon has to have 8 neutrons. So whatever's inside that nucleus is what's making these atoms of the same element fundamentally different. So they're not all common in mass and size. So for example, this carbon-12 is the smallest, carbon-13 is in the middle, and carbon-14 is the largest because it has the most number of neutrons, adding to that dense, positively charged nucleus. Speaking of these subatomic particles, there had to have been people that did experiments to come to these conclusions, and let's go through those briefly. The first one we have is J.J. Thomson with his fundamental work with what's known as the cathode ray tube. And with the cathode ray tube, Thomson was able to determine that within an atom, there has to be some sort of particle there, and that particle has to be negatively charged based on how the deflection of light had occurred when you're putting a magnet to it. So essentially they were finding that he was putting a positive end towards this tube, and then the beam of light would go towards it. So if we know that opposites attract, if I put the positive end here, and if I were to put a negative end here and it were to go away from it, forgot the word there, we would find that this has to be negative. And then as a result of that, they found that they're very small in size, so it has a big charge to mass ratio, because high charge, it's very negative, but it's very, very small. To further quantify that amount of charge, Robert Millikan is known for the oil drop experiment, which led to essentially realizing that, okay, a charge of an electron relative to, the atom is going to be a -1. And there's actually a value for this, but you don't need to know that for the course. And then next, if there's negative, there has to be some inherently positive thing in the atom to kind of balance this charge out, which Thomson claimed that were the case because he basically said in an atom, there's all these negatively charged things, and then as a result, the whole thing is positive to kind of balance it out. This is called the plum pudding model, because being that he was British, plum pudding is a popular entree / dessert there. So plum pudding was his model. Rutherford disproved the plum pudding model as a result of the gold foil experiment, where basically they shot alpha particles. Alpha particles are positively charged particles at a piece of gold foil, and what they found is that most of them went through. However, some of them deflected and went the other way, or some of them deflected and went back this way, which basically led to the conclusion of two things: that the atom is mostly empty space where things can pass through, but occasionally it might hit something positive and kind of deflect and go in other directions. So this basically led to the conclusion that there has to be a densely packed positive nucleus in the center of an atom, which basically to us means that there's got to be protons there. Moving on from that, we have some other developments in atomic theory. Bohr was the first person that really thought of modern atomic theory by adding quantum theory to it, which is a relatively new idea during this time period, and basically saying that if you have a nucleus here, the atoms or the electrons have to be in discrete specific orbitals that go around the nucleus. So maybe you have this first level and the second level, and then maybe you have a third level, and so on and so forth, similar to our solar system. So of course, you got to think of the time period. Solar system planetary models are very popular, so Bohr just wanted to add his as well, and it fit to current research that they were familiar with. Schrodinger introduced the quantum mechanical model, really started to introduce mathematics into the wave function with regards to electrons, and identified that electrons exhibit wave behavior. And then lastly, we have Chadwick in 1932, who had done a series of experiments to essentially deduce that it's not just positive in the center in the nucleus, there's also some neutral body that's there, and that's our neutron. And he did several experiments with charged particles and polonium to deduce that. So that's going to wrap up this video.